So the current of two bulbs in series would be 1/2 the current of one bulb. Or actually, I won't even need that parentheses. 1/2 of the current of one bulb. We're going to keep comparing to the original one bulb. Close enough. As far as power in series, so power in series is equal to our current squared in series times our equivalent resistance in series. I just put this in for my current in series. I can actually take that current and double it. Actually, but instead, since I want to take this back to EMF and resistance, I'm going to take this. EMF over my equivalent resistance is equal to the current in series. So E over R equivalent for my series the series. If you don't believe me, too bad. So that's got to be squared times the equivalent resistance in series. You could distribute those as you do. Ooh, one thing I do need to mention. Our equivalent resistance in series. Equivalent resistance in series was 2R. So I can have this value equal to 2R. So E over equivalence in series, 2R. Those are both going to be squared. Extendo, extendo. Now I can distribute that square. I get E squared over 4R squared times 2 times R. Obviously, there's some canceling that can happen. I can get rid of that. I can get rid of one of those. 2 over 4, that's the same as a half. 1/2 E squared over R. 1/2 E squared over R. Relate this back to the power of one bulb. What was the power of one bulb? It was E squared over R. Okay. E squared over R. So this ends up being the power in series ends up being 1/2 the power of one bulb. Okay, one more to do. That's the parallel resistance. Compare these back to our original bulb. So our current in parallel. Ooh, that's not good. Oh, it's even not gooder. P-A-R-A-L-L-E-L. Parallel is equal to our EMF over our equivalent resistance in the parallel circuit. If I relate this back to, yet again, our equivalent resistance in parallel. What was that? What was that? What was that? What was that? That was R over 2. So, move forward. Extendo Pageo. Is equal to my current in parallel. If I do some rearranging, let's see. Well, if I could relate, I have to relate this to the current of the one bulb system. What was the current of the one bulb system? It was E over R. So how does this relate to E over R? Pretty closely. Divided by 2 puts 2 on the top, so 2 times, and I said the current on one bulb was E over R, so 2 times the current on one bulb by putting them in parallel, equivalent current in parallel. Ooh, that's pretty nasty, but it'll work. Power, last one, comparing our power in parallel to our power for a single or a one bulb circuit. So power and in parallel, I'm just going to do that. That's way easier. Is equal to I squared in parallel times equivalent resistance in parallel. Well, relating to EMF and R, right here, I have that my current's equal to this. My parallel current is equal to EMF over R over 2. So really 2 times E over R. But that whole thing's going to have to be squared. Our equivalent resistance in parallel. I said that earlier. Equivalent resistance in parallel was R over 2. So I can say R over 2. I can distribute out the square. So I've got 2 times 2, or 2 squared, not 2 times 2. 2 squared is 4. E squared, R squared times this value R over 2 is equal to my parallel power. We're going to have some canceling happening like crazy. One of the R's can go away. 4 over 2, that sounds like 2 to me. 2 times E squared over R. I want to relate this back to the power of one bulb, which was E squared over R. Here I am at 2 E squared over R. So I am using 2 times the power of one bulb. Ooh, that's a B. That's a lot. That's a lot. What do we learn from this? All right, so if we have a one bulb system, we have a current, we have a power. If we take those bulbs and put them in series, our current in series is half of what it would have been in one bulb. And our power is half as it would have been in one bulb. In parallel, we have twice the current as in a one bulb system and twice the power.